Okay, so vectors. So yesterday we looked at what a vector was. We're going to write them with this symbol over top, V with the arrow, and the magnitude of the vector is written with the bars on the side. And two vectors that are equal in magnitude, and they go in the same direction. Two vectors that are in opposite directions but with the same magnitude are the negative of each other. And a vector, two vectors in the same direction, one is twice as long as the other. Well, the vector 2v has twice the magnitude of v. Okay, so the magnitude of vector 2v is twice the magnitude of v, so you can take the 2 out. This is called a scalar multiple of a vector, so 2 times a vector. Could be 3 times a vector, 4 times a vector, whatever you want. 2.7 times a vector. Okay. Now, the next thing we looked at is vector addition. So vector addition, we have two laws, the triangle law and the parallelogram law. The way we looked at the triangle law was just the top half of that triangle, and to add these vectors, we take one vector, start with v, and then we place the other vector at the end of that vector, and the path from the beginning to the end is the resultant vector. Okay, so it's called the resultant when you add or subtract two vectors, two or more vectors. Okay, so the resultant is v plus u, and it's the shortest path taken. Okay, you could also do that from the other side and start with vector u. Well, vector u here is going to be parallel to this vector u. So it's going to create a parallelogram, and if you add u plus v, you're going to get the same resultant vector, which is quite nice, that v plus u equals u plus v. Okay, this creates a parallelogram, which leads us to the parallelogram law over here. If you start both vectors from the same point, so they start from the same point, and then you complete a parallelogram with the two vectors, so making a vector parallel to u at the top here with a dotted line, and a vector parallel to v across over here with a dotted line, and you make a diagonal in the parallelogram, that is v plus u, also u plus v. Okay. So the next question we have then is, if we know what v plus u or u plus v looks like, is what does v minus u look like? Okay. So what does v minus u look like? Well, negative u is the opposite direction of u, but the same size. Okay, so v minus u is going to look like v plus negative u. Okay? So this is basically what you have. The magnitude of u is the same as the magnitude of negative u. If u is this vector, then negative u just goes in the opposite direction, same size. Okay. And we can write v minus u as v plus negative u. Okay, so if there's v, and there's u and negative u, when you add them, or when you do v minus u with the triangle law, this is what you've got. Okay, so v, right, v here plus negative u, and the resultant is here. It's the shortest path from the beginning to the end. Okay, so that's using the triangle law. Using the parallelogram law, we have something slightly different. So if we make v and u starting at the same point again, If you use the parallelogram law to add these two, v plus u, I would make a diagonal across here, right? And I would go from where these two join to the end over here. But if you want to do vector subtraction and you just want to write down v and u, and you want to see what it looks like, it's the opposite diagonal. So there's only two diagonals in a parallelogram. So these two vectors u and v make this parallelogram. U plus v is along here, and v plus u is along there. V minus u is the opposite diagonal. The only complicated part to this is, okay, it's the opposite diagonal, but what direction does it go? Does it go up or does it go down? Okay. So it always heads towards the vector that you start with in the subtraction. Okay? So v minus u goes from the end of u, so the tip of u, to the tip of v. Okay? And there's a reason for that, and the reason is the triangle law. So if you look at this v over here and negative u here, if you look at the parallelograms working from there, then you can see that v plus negative u is this vector. Okay? So depending on which law you're using, you have two different ways of looking at it, but you can always see it from the triangle law. So we've got the addition of vectors, and now we have the subtraction of vectors. Okay. Next thing we want to look at is point-to-point vectors. As I said before, vectors don't really have starting points. If two vectors are equal, it means they're equal in magnitude and direction. They can start at any point. But if we want to give them starting points, that's okay. We can give them a starting point and an ending point, and that will help us define the length of the vector and the direction of the vector. Okay? So if I say I'm going from a certain point in this classroom to another point, and it's 5 meters diagonally across the classroom, and somebody else is going in the same direction but starting from another point, our vectors are the same. Our paths aren't the same, but our vectors are the same. Okay, so as long as it's the same direction and magnitude. So to define a point-to-point vector, well, you need points. Okay, and start from this. So if I make points A, B, and C, then we can define the vector from A to B as AB. Okay? So it's two letters, the starting point, the ending point, and that helps you determine the direction and the magnitude of it if you know where those points are. BA then would be the vector in the opposite direction, from B to A. So we now know that AB is equal to negative BA. Okay? Or the negative of AB is BA. If you're going to add these vectors, CA plus AB, just looking at these vectors, CA plus AB, using the triangle law, would give me the vector CB. Does that make sense? CA, so this vector up the side here, from C to A, and then you add the vector AB, so you're putting one vector on the tip of the other one, and the shortest path would be then from C to B. So when you're looking at it more algebraically, CA plus AB ends up being CB, and as long as the letters in the middle here are the same, and it's addition, it's like they cancel out. Let's talk a little bit more about scalar multiples of vectors. So scalar is just a real number for our purposes. Okay. So 2v equals a vector in the same direction as v, but has twice the magnitude. So we've talked about that already. So that is 2v equals, the magnitude of vector 2v equals twice the magnitude of v. Okay. 2v is itself a vector. Okay? You could call it something else. You could call it w. Okay, but 2v is itself a vector. So when you're taking the magnitude of the vector 2v, you need to put the magnitude on the outside of it. It just so happens that logically it's twice times the magnitude of vector v. Okay. Negative 2v is 2 times the negative vector. Okay. That's a vector in the opposite direction of v with twice the magnitude. And here's some pictures of what it might look like to add or to subtract vectors that are scalar multiples of an original vector. Okay, so if that's u and that's v, this is an approximation, but that would be 2u and 3v. And if you want to do 2u minus 3v, well, I'm using the parallelogram law here. I'm going to end my vector at 2u, and I'm going to start it at the end of 3v. So it's not addition. Addition would be right across from the starting point where these two vectors are connected to the opposite vertex. Here it's the other diagonal. Starting from 2u, or starting from the end of 3v, going to 2u is the resultant vector. Okay, two vectors are collinear. Kind of means they lie on the same line, right? Well, we have a vector definition for that. Because vectors don't really have a starting point, or don't have to have a specific starting point, for two vectors to be equal. Okay. We have this definition for collinear. Okay. Two vectors are collinear if they lie on the same line when they start at the same point. So that is u equals kv, where k is a scalar, a real number times the vector. Okay? So if vector u is 3.7 times vector v, then they are collinear. If vector u is negative 2.9 times vector v, then they are collinear. Okay? So unit vectors. When you studied the unit circle, what did the unit mean? 1. Yeah, so it had a radius of 1. So a unit vector, what do you think that might mean? Vector with magnitude of 1. Okay? So a unit vector is a vector with length 1 or magnitude equal 1. Okay? We have a special symbol for a unit vector. If we know it's a unit vector, instead of putting the line with an arrow above it, we put a little hat on it. Okay? So it's a unit if it's u with a, or v or w or whatever with a hat on top of it, then it's called a unit vector. We know its magnitude is 1. Okay? Now, if you had a vector of length 3, what would you multiply that vector by to make it length 1? Pardon? A third. Okay? If the vector had a length of 1/2, what would you multiply it by to make it length 1? Okay? If the vector had length k, what would you multiply it by to get length 1? 1 over k. Okay? So for any vector u, to get a unit vector that is collinear with that, you multiply it by 1 over its own magnitude. And that would get you a unit vector. And the simplest vector there is the 0 vector. It's nice to have a vector that if you add to another vector, doesn't change it, right? We haven't talked about multiplying vectors yet, and we won't for a little while. That's a little bit more complicated. But in terms of adding vectors, if you add the 0 vector to a vector, you want to end up with the original vector. If you subtract a 0 vector from a vector, you want to have the original vector. Okay? So we've defined it as this. So 0 with an arrow over top of it is a 0 vector. Its magnitude is 0, and it has no direction. Okay? If it has no length, it has no direction.